No, further Lagos, Kwara, Lagos, Kwara. But Kwara yẹn is supposed to be three. It's supposed to be Lagos, Kwara, and now Kwara àti Kogi wọ́n ti wá pápọ̀ sí under Kwara. So now, Kwara yẹn now, you have Kogi. Kogi is essentially the scene at Ayétòrò. So, but when you talk of Kogi, irú bẹ̀rẹ̀ Ayétòrò is they are the conservative part. No, it's market survey. So we now want to see whether education will influence the influence of education on the market. Or whether it will take for this where now so that yes, we have our where the state or the technical course no influence anyone. Where so
So you are welcome.
Now for some of them that said okay, like okay, for some to say okay, they prefer the interlocks compared to normal one. Is that preference? Is this statistically significant to go into production? We just want to see shape the young we go into the production of that composite interlocks compared to
So you are welcome to this class. So I think we can announce that in our last physical class, we are talking about some properties of real number systems. These real number systems are some properties that were first discussed on the real number, after which researchers of today are now depending on it and now making more properties under it. So we have talked about the dense property and the Archimedes theorem. So today we'll be looking at another properties of real number system called the absolute value properties. So when we say the absolute value properties, it is defined as follows. They are going out now. I'm locking the door. I'm stop opening that door.
Sorry, sir.
So the absolute value, when we say absolute value, we are referring to so let x be a real number and so the absolute value of x is denoted by this, okay, and it's defined by so we have defined absolute value as the number absolute value of x. It is x if x is greater than 0, and if this is 0, okay, it means x is 0. And if the absolute value gives negative x, it means x is negative. Okay, so these are the three properties of the absolute value properties. So when next we are talking about the definition of absolute value, you can find it as this. For example, if in other words, absolute value of x okay is simply this. Okay, so we can define the absolute value of x as this, such that if x is any number in R, if x is negative 2, for example, okay, this is equal to okay, so excuse me 1 minute. Sorry. So let me know if you have any questions so that I can. If there is any question. Okay. So if, for example, we select x to be negative 2, okay, and then we substitute x into this formula, what we get will be the square root of 4, and this will be what? 2. Okay. Even if we select x to be 2, this is simply a 2 square, and of course this is also what? A 2. Okay, so anytime we are dealing with the absolute value of a number x, where x is a real number, okay, the result is always positive. Okay, and we can see that from here that if this gives x, okay, it means x is positive there. And if it is negative x, it means this x itself is a negative number. Okay, so if this is negative and x is a negative number, it means this negative will affect the negative inside this x, and that will make this positive. Okay, so anytime we are finding the absolute value of a variable x, okay, it is usually a non-negative value. Okay, so before we go into the properties of this absolute value, let us also see some examples. Okay, in addition to what we have here. So if you are given, for example, a particular inequality of absolute value, that is x is less than, absolute value of x is less than 3. How do we interpret this in terms of the formula we are discussed earlier? Okay, so according to the formula, let me just recall the formula somewhere here, then I will use that to interpret this. We have said that this can be positive if x is positive, and it's negative x if x is negative. Okay, if x is negative, so if this is minus x, it means x is negative. Now let us interpret this in terms of what we have here. Okay, so it means in terms of this is, if we remove this absolute value, it means we can have this, and we can also have this. Okay, so if you want to interpret this becomes x is less than, okay, if we take negative from both sides, this will be minus x, okay, greater than 3. Okay, and from what we have here, okay, let's do it this way. Sorry. Yes, this is the interpretation of this. If this is x, okay, it will be less than 3. And if it's minus x, it will be less than 3. Okay, so in terms of the second term here, this means x is greater than negative 3. Okay, now let's combine both this and this together. The interpretation here also means minus 3 is less than x. Okay, so let's call this 1 and let's call this 2. Okay, so by combining 1 and 2, so if we combine s less than 3 and minus s less than 3, okay, minus s less than 3 is what we have here. Okay, now we're going to combine this 1 and 2 together. So this means that minus 3 is less than x. Minus 3 is less than x, and this that's from 2. Okay, and then from 1, x is less than 3. From 1, s is less than 3. Okay, so what you are saying in essence is that if we have an absolute value of x less than 3 like this simply means that minus 3 is less than x less than 3. Okay? So under the absolute value, anytime we have a term of this form, it simply means this. Okay? And vice versa, if you are given this means this, and that's the meaning of this by implication. Okay? So, in summary, if x is a real number and a is a positive number such that the absolute value of x is less than a, okay, by the virtue of this example, what it means is that minus a is less than x and is less than a. Okay, that is in summary. Okay, anytime we have absolute value of a number, it simply means minus a less than x less than a. Okay, so having noted this, we also note that for any x in R, okay, two things is certain. Firstly is that the absolute value of x is usually greater than or equal to x. That is, if you pick any number here and we take the absolute value of that number, okay, the absolute value of that number will be greater or equal to x. So we pick the choice of equality because of 0, because it's possible for us to pick 0 in the NAP, okay, and this will also be satisfied. And secondly, absolute value of x is greater or equal to minus x, okay. These two things are obvious from the definition of absolute value. Now, in what follow, we will be talking about properties of absolute value one after the other. I think we will be discussing about 8 of them here. Okay, so let's take them one after the other. But before that, please kindly note this. Please note that before we proceed. Okay. So if you have any question, let me see your comment there so that I can respond. No question yet. People are saying good afternoon then. Okay. So no question yet from the comment I have there. So let us proceed. So now we want to take some properties of the absolute value. Okay, so there are many of them, but in this class we will be looking at just 8. Okay, so as usual, any properties we define here, we will try as much to show how they are like that. Okay, so let x, y, z be element of R. Okay, and alpha, comma beta are scalars. So then 1. So I'll start from the obvious notes that we have earlier, that the absolute value of x is greater than or equal to x, and the absolute value of x is also greater than or equal to minus x. Okay, this is also valid for y. If I'm using the variable y, okay, we can see that the absolute value of y is greater than or equal to y, and absolute value of y is also greater than or equal to minus y. We can do the same for z, okay, but we are using the variable x here alone, okay, just for the reason we'll see later. Okay, so 2, the absolute value of x plus y is less or equal to absolute value of x plus absolute value of y. Okay, so this is the second properties. Okay, and from here one can also have this. Okay, let me call this 1a, then sorry, 2a, then let's have the b part. The b part says absolute value of x minus y is less or equal to absolute value of x plus y. Okay, so number 3, the absolute value of xy is the same thing as this. Okay, the absolute value of xy is equal to this. So also, if we have the absolute value of alpha x, because we have defined alpha as a scalar here, okay, and x is a real number. Okay, also this becomes this. So, but provided alpha is positive. Okay, so the absolute value of alpha x is equal to this, provided we can have alpha to be this, provided alpha is positive. Okay, and number 5, we can also have the division form that says we can split this like this. Also provided the denominator y is not equal to 0. Okay, so this is the 5th property. Okay, also we can deduce the fractional form here, that if you have this also, if you have this, you can split the absolute value on them. Okay, like this, but here we can remove the absolute value. Okay, provided alpha is positive and x is not 0. Okay, so again, 7, if you have the absolute value of the absolute value of x plus y plus z, okay, this will be coming from the virtue of 2 here. Okay, this is less or equal to okay, so this is coming from the virtue of 2. And similarly, 8, if you have x, y, z, this is similar to the absolute value of x, absolute value of y, and absolute value of z. Okay, so we can continue this way, okay, by the inclusion of beta, okay, in some cases, okay, and for example, if we have, let's call this 9, if we have alpha x plus beta y, this is less or equal to this, plus beta y, okay, and invariably by the virtue of 1 here, of 2 here, we can break this into this form, okay, and by the virtue of this property, this can be alpha x then beta y, okay, so we can move on and on, okay, to deduce some properties under the absolute value. So now let's look at some of the proof of these properties. Okay, so number 1 here is obvious from the definition, so we won't prove this, but we'll try as much to prove other ones. Okay, starting from here, then this and this. Okay, so let's take them one after the other. So, proof. So, let's have this. Okay, someone is commenting. Let me get. Okay, the ring light. Let me off the ring light. Let me know if this is okay. Is it okay like this? Okay, hold on. Someone is talking about VI not having under the VI. If I can recall what is there. Okay, this is okay. Let's have what or IV. You are referring to IV there. Okay. You will recall that we said this alpha is a scalar. Okay. A scalar can either be a positive number or a negative number. Okay. But by the properties of absolute value, we can split this on this. Okay. We can split this on this. Now, if I want to write this alpha without this absolute value, okay, that is if I'm writing this as this, okay, this means that this alpha is positive. Okay, it means the alpha there is positive. Okay, and the reason is that I'm removing this. Okay, by removing it, okay, it is positive. Okay, I think I get the message there. The person that asked, somebody asked the question earlier. It is, I'm removing it and imposing a condition on it. Alpha greater than 0. Okay, I think that answered the question there. Okay, now let's proceed to the proof of. So we are unable to get if you rub it off. Okay, since it's a, okay, the video will be recorded online. Okay, you can go through it after the class. It's possible that you go through it. So now let's take the proof one after the other. If alpha is less than 0, does that mean it is negative? Yes, it is negative. If alpha is less than 0, it's negative. And negativity doesn't happen here because of the absolute value on alpha. So thank you for that question. Should we add the absolute value to the alpha? Then, yes, the absolute value is on alpha. So we don't want to put it. That's why we remove it. And by removing it, we must turn the alpha to positive number. We must surely do that. Okay. Abiola, or who is that? So just let me know if you get it by saying okay. All right. So let's move on. So let's have the proof one after the other. Now, the first property is under the absolute value. We have said that is obvious. Okay. The IX. Any question on that? Hello, Kiri Akorede. What do you want to know about it? This is a property. Okay. By the virtue of property 2, we said we can split this into 2. Okay. Then by virtue of property 3, that says we can split this. So there is a property that says we can split this as alpha, and we can split this as x. You can also split this into 2 like this. There is a property that says so. Okay. So now, for the reason I just explained, I want to write this as alpha, just to show that it's a scalar. It's different from x and y, and similarly for beta. Okay, I'll be writing this as alpha. Then that x, because it's a variable, will be under the absolute value, and then I'll write this as beta. But then I must write the condition that alpha is greater than 0 and beta is greater than 0. Okay, because sometimes those the variable x here sometimes may be a vector. Variable x and y sometimes may be a vector. Okay, so that is that. So let's have some of the proof of those properties before we move on to another thing. All right, thank you. All right, understood. Saints, all right. So now, I will be starting from property 2 because the first part there is obvious. That's one. So property 2 now says, now suppose x comma y is a null. Okay. Let me complete the statement. Suppose that x comma y is a null. Right. By property I, property I says what? So from property I, if you have them in your B or something, you say property I says absolute of x is greater than or equal to x. Then I'm picking the variable y now. Like if we also have the absolute value of y, that will be greater than or equal to y too. Okay? So now I'm adding these two terms together. By adding, we get, I want to add these two inequalities together. And we can add them together because both of them has the same order. The same order of inequality that is greater than or equal to. Okay? So it means I can add this and this together. And that will be x plus this. Then the inequality, because this is since they are the same, this will be x plus y. Okay? Or we can interchange this to be x plus y is less or equal to this. Okay? Again, property I says talks about two things. Property I talks about two things. Okay, we have used one of them here. So again, from that property I, this is greater than or equal to minus x, and it is also greater than or equal to minus y. Okay, again, if we add this again, by adding this, this is what we have. So we add these two again. We get, so I'm labeling this now to be A. What we have here, I'm labeling it as A. Okay. Okay, so we can interpret this further to say that, negative is common here. If we factor out the negative, okay, and then multiply both sides by negative number, this will be, I hope we all get that. I'm multiplying both sides by negative. So negative will affect this entire term, and it will be this. Okay? So because I'm multiplying with negative, this inequality will change to less than. And of course, if I multiply this with negative, this will be what? X plus y. So I will call this place B. Okay? Now, there is an example we considered earlier that will enable us to combine both A and B together. If we combine both A and B together, now from B, let's say by combining both A and B, so from B we have that minus absolute value of x, okay, is less or equal to x plus y. That is from B. That is the statement we have from here. Okay, but we have a similitude of this in A that says x plus y is less or equal to this. Okay, so what you now have here is this. We have the range of minus this, okay, less or equal to x plus y, less or equal to this. Okay, this now look like what we have earlier. What we have earlier as a in one of the examples that we say that minus a less than x less than a. Okay, And there we say this gives what? We say this gives absolute value of x is less than a. Okay, that was the last example we considered. Okay, so it means we can also decide to take this back to the other form to have something of this nature. So let's see that. I'll be writing that up here. So I'm just using this as example because I have considered an example that look like this. Okay, so if we combine this, if we combine what we have here, okay, what we have here simply means that that's by virtue of example 1. This simply means absolute value of x is less or equal to absolute value of x plus absolute value of y. Okay, that's by virtue of example. By virtue of example 1 or example 2 thereabout. Okay, so that's how we prove that property 2 there. Okay, so let's see property 3. So any question on that? No question. So let's say another property. So another property, that's a property 3. So if you have two variables, we have completed this here. If you have two variables and we are taking the product of the two variables under the absolute value, okay, by definition of absolute value, okay, let's start this way. Let us start this way. Let x, y be element in R. Let x, y be element in R. So by definition, absolute value of x is equal to x squared, and absolute value of y is equal to y squared. Okay, so here if we now have the absolute value of xy, okay, under the same absolute value, again by definition we can interpret this as the square root of xy all square. Okay, you can interpret this as the square root of, okay, when we have a term, okay, we say the square root of what? X squared. Okay, because this is a single term. Also, xy is also a single term. After the multiplication, they become a single term. Okay, then by definition, we have this also to be this. Now, by law of indices, xy takes from this power. Okay, and this will be x squared. Okay, so by indices, okay, by the third law also, we can split this into 2. So that we have something of this nature. So by the third law. So by definition that we have said earlier here, this is what? The absolute value of x, and this is the absolute value of y. Okay? So that is why we say that, that's why we say the absolute value of xy is equal to this. Okay? I think that one is straightforward. So property 4 follows from here. If we have one of these to be alpha, that is a scalar multiplying x. Okay, it's the same form, but at the end, if alpha is a scalar, okay, if alpha is a scalar, for example, if alpha is a scalar, I'll take the absolute value of alpha. Okay, we know this to be this. Okay, who can tell us the answer to this? The answer to this is not simple. If you are writing it as alpha, okay, it must come with the condition that alpha is positive. Okay, so we must come with the condition that alpha is positive. Okay, because when you take the absolute value of a term, it do not remain the same. When if you take the absolute value of, so it is not good. What we are saying in essence is, if you write this without condition, without any condition, this is not true. Because alpha can be a negative number. If alpha is a negative number, okay, can we say this happens? No. Okay, it will not happen if this happens. Okay, and of course, if you say absolute value of 2, this is also 2. This happens. Okay, so anytime we are writing this as this must come with the condition that alpha is greater than 0. Okay, and I think with that one can prove the property 4 there. Okay, I think the next one, which is more interesting to prove, is that of the division. Okay, and that also follows from these properties. Okay, so let's see that also quickly. So also, is this 5 or okay? So by definition, this is square root of x over y. Okay, by law of indices, one can say this is x squared and this is y squared. Okay, and we can split the square root on each of these. Okay, but this must come with the property that y is not 0. I think we have said that earlier. And of course, if y is not 0, this is possible. Okay, this is how we prove that also, and host of other ones there. Okay, so now the property 6, I think is this 6 also follows from here. So the property 7 is of 3 variables. Okay, we'll prove property 7 the same way we prove property 2. Okay, and we will prove property 8 the same way we prove property 3. Okay, all we need to do is to extend the variable there to 3. For the case of 2, you have done that in 2 and 3. So for the case of 3 variables, okay, you just the same condition, same pattern of proof. Okay, so maybe when else we meet at the physical class, we can demonstrate that, and then let me see that. Okay, so if there is any question on this, let me know, because I'm about to set another thing now on the properties of absolute value. Any question? Okay, no question. Okay, somebody said last one I should come back again. I don't know if you are referring to this. Are you referring to this? Comment again, let me see. No question, thank you. All right. So let us also see one of the one of the concepts we usually use in this course. And the concept is, it will be stated in this lemma. Lemma 1.7. The last definition is definition 1.6. So now we want to have a lemma. So a lemma is like a lesser law in mathematics that we usually use to prove a theorem. Okay? So in the future of this course, we'll be using this concept to prove many of our theorems. Okay, and it states thus. Can you please repeat the alpha proof? So we can't repeat it. Okay, you can actually rewind and then check to you can actually rewind the video to the alpha proof. Okay, you can rewind and then if you didn't get, so you let me know when we meet at the physical class. So thank you. So now, I want to state one of the lemma that is usually useful in this course. The lemma goes thus. The lemma is under the absolute value properties. So we say let x be a real number and epsilon is a positive number. Okay? So if we have these two conditions and this absolute value of x is less than epsilon, okay, then x is 0. So if x is a real number and epsilon is a positive number, and this condition holds for the two terms that we have here under the absolute value. Okay, so there is no choice for x other than x is 0. Okay, so this is an established lemma, and we prove that here using the proof by contradiction approach. Okay, so let's quickly see this and then we'll make we'll just take a corollary on this. Okay, so let's see the proof. Okay, let's do this way. Suppose by contradiction that x is not 0. What we are trying to do here is to prove this by contradiction. What you have said here is if this condition holds, then x is 0. Now we want to prove by contradiction and see whether if this condition holds and x is not 0, we want to see whether that is okay mathematically. Now we say, suppose by contradiction that x is not 0, and we want to still hold on this. X is not 0, and we want to still hold on this. We want to see what will happen. Okay? Now we have said that x is not 0. We want to see whether this goes with this. Now choose epsilon to be equal to 1/2 or any positive number. You know, when we say a positive number is any number immediately after 0. Okay, immediately after 0, that will be, let's fast forward to 0.1. It's fast forward anyway. It's not the number after 0 is not 0.1. Okay, but let's say it's 0.1. You can say it's 0.2, then 0.3. Okay, move forward. So here we are picking 0.5. Okay. Okay, it's a continuation of properties of absolute value. The properties of absolute value we just discussed. Okay, that's what the lemma is talking about. Okay, so somebody is saying 0.3. 0.3. All right, 0.3 should be 3/10. Are you okay with this? Yusuf Hashim. He said we should use 0.3. 3/10 is 0.3, right? Please comment. Yusuf, I'm waiting for you. All right. Okay, so we choose S1 to be 3/10. Okay. Now recall this. Recall what we have here. So then, absolute value of x will be what? Less than 3/10, according to what we have here. Okay, we are choosing S1 to be what? 3/10, and this is what we are using this now. That absolute value of x will be less than this. Okay, now under the properties of rational numbers, under the absolute value of rational numbers, okay, we say we can cross multiply this. That is, if you have a rational term, I can say 10 multiplied by this. Then this means something here is over 1. This is like over 1. Okay, so this implies that 10 multiplied by, okay, less than 3. Okay, I think we have said, though this is obvious anyway, cross multiplying under the price of rational numbers. Now, this is 10. This is absolute value of x. Okay, less than 3. Is this possible in math? Is it possible that 10 times a non-negative number is less than 3? It is not. It is not, because absolute value of x is a positive number. Okay, though we have said x is not 0. If x is not 0, assume x will be any number here. Any number. Okay, if you assume x will be any number, it's usually it will be a positive number. So 10 times a positive number less than 3. This is a no. Okay, I'm putting dash on this. Okay, 10 times this can never be less than 3. Okay, so somebody said I should repeat again. I think you get it from here. We are making S1 to be 3/10. Then we say this according to what we have here. Then if we cross multiply, since we say x is not 0, by our contradiction, this is what we have here. If we cross multiply, 10 times a positive number can never be less than 3. Okay, so this is false. This is false. So therefore, but if you pick x to be 0 here, what will happen? The condition will be satisfied, because 10 times 0 will be 0. So 0 is less than 3. Are we there? So yes, I got it. That epsilon is a constant. Okay, it's a constant, and it is a positive number. Okay, and I say a positive number started from a number immediately after 0. That's why somebody suggests we should use 3/10. I'm picking 1/2 earlier. Somebody said we should use 3/10. Okay, even at that, it will not hold. So there is no choice. There is no choice of x. Or there is no. Let's write the English properly. There is no other choice of x except X is 0. If X is 0, okay, no matter what number you pick here, the condition will be satisfied. No matter no matter the choice of your number here, it will be satisfied. And that's why we come with the lemma that says, if you have this condition, S must be 0. Okay, I think that is clear. Yes, S must be 0. That is it. Okay, so there is no other choice. So must X be equal to 0? Yes, for this condition, it must be 0. Bamidele Mohammed. So for this condition that we have here, X must be 0. Okay. So this is just a proof by contradiction. Okay, but here is the law. This is a law. Okay, it's a law in mathematics that has been established. Okay, we are just given a kind of true if X is 0. Yes, true is yes. Let's try half. Yes, I've done that before. Somebody said we should try 3/10. It's the same thing. You can do that by yourself. The testimony, Emmanuel. Try it. If you try it, this will be 2 times this. Okay? 2 times this less than 1. It is not true also. Can we use the whole number instead of rationals? Yes, we can. If it is true for that rationals, it is true for a number. That one is obvious. Okay, it is obvious. Okay, where the condition is not obvious, is that of the small numbers, and that's why we are picking small numbers here. Okay, is that taken? So let's have a lemma for this before we. Sorry, let's have a corollary. Corollary now. Now, corollary is like a deduction. Yes, we are continuing. Yusuf Ashi. Now, corollary 1.8. Let X belongs to R and epsilon is positive. Okay, so if there exists a non-negative number, if there exists a non-negative number alpha such that the absolute value of x is less than this. Okay, you know, earlier we usually have x and epsilon, and this will be absolute value of x less than epsilon. Now, if we introduce another, yes, corollary are like deduction from already established fact. That is a fact. Now we are deducing something from a fact. That is corollary. Is that taken? Raji, is that taken? All right. So this follow from the. All right, thank you. This follow from the lemma we have earlier. This rule from the corollary we have earlier. In fact, if this alpha is 1, if alpha is 1, okay, this is exactly 7 that we have earlier. Okay, so that is that. So if you have any other questions, if there is none, let's move to the fourth properties under the real number system. No question. Okay. So the fourth property is referred to as the Dedekind theorem. Okay, the Dedekind is a name. Okay, and the theorem was named after the mathematician, and that's why it is referred to as just like we have Archimedes theorem in our earlier class. Okay, so we also have one referred to as this. Okay, what this simply means is that this person was trying to describe a particular number on the real number line. Okay, and that is when we first discovered the first irrational number. Okay, so let us first describe what the theorem is talking about, then before stating it. So if you have a real number R, okay, and there is a number at the middle here, not necessarily 0. I call the number here alpha. Okay. Okay. The properties we are talking about here in this class are 4. Okay. Absolute value is just 1. So under absolute value, there are properties under it too. Dedekind is another 1. Archimedes another making 3. Then the dense property making 4. Earlier in our physical class, we have discussed 2. Okay, for today, this is the second one we are discussing. The first one we discussed is the absolute value properties. Is that taken? Samson. Okay, so now, so on the number line, there is a number E on the number line, okay, which separates this line into 2. Okay, now, okay, so let's call this part. Okay, I'm referring to this number here is alpha. Okay, then from here to here, we are calling this part A, this part B. Okay, and there is a number at the middle here that break the line into 2, such that one part is A and the other part is B. Okay, so if I say the supremum of A here, the sup of A here is alpha, isn't it? The supremum of A is this point, and while the infimum for B is also this point. Okay, it means both of them have something they want to talk, they want to share, but the assumption by the Dedekind theorem is that if we take the union of these two numbers, of the two sets, if you take the union of these two sets, it is out. And if you take their intersection is empty. It means The numbers here are different from the numbers here. Okay, we only know that they meet at one point. Okay, and the number is alpha as we have here. So the assumption of this theorem is based on these two ideas. A union B is R, A intersection B is empty, meaning they have nothing in common. So when we combine them, they form the real line. Okay, if this happens, okay, what the person is now proposing is that if you have any element that is less than alpha, okay, if you have any element, that element is in now, and the element is less than alpha, that element is here. If you have any element in now that is greater than this alpha, the element is there. Okay, and that is what the property is talking about. Okay, it's an observation by the earliest mathematician. Okay, when they first discovered the irrational number, and since then the theorem or the assumption was called Dinikin's theorem. So that number that breaks the real line into two is referred to as the alpha cut. Alpha cut. Okay, to cut something. Okay, alpha cut. Okay, because it breaks the line. So let's see the theorem properly, and then a simple proof on this. Okay, and there are other. Sorry, somebody is saying something. I want to try to get. Okay, so let's set the okay. So you will recall that this is how I've described the line earlier. So now, okay, somebody is answering, you're answering the question to other person. Yes, this is a fourth property under the real number system, not real number, the real number systems. Okay, so the further says if A is bounded above by B, if A is bounded above by B, okay, there is a number, in the nav. So there is a number, we call the number alpha, okay, or let's make it look, there is a number alpha in nav. There is a number alpha in R such that x less than alpha implies that x belongs to A and x is greater than alpha implies that X belongs to B. Okay, so this is exactly what we are talking on the number line that we use here. Okay, if all these conditions are met up to this level, A is bounded by B. It means on the lower part we have the set A, on the upper part we have the set B. Okay, it means this question now says if you have a particular number in now, okay, this number is at the middle of that place where A and B is supposed to meet. Okay, if you have any element in now, okay, that element, if it's less than X, okay, that element belongs to A, and that element is is greater than alpha, the element is in B. Okay, so the proof is just straightforward as we have them here. Okay, and the proof is the same way if we want to prove this. Okay, in the proof we just assume all this up to this level. Okay, in the proof we will assume that all this happens up to this level. Okay, and then from here we'll start again. So let's see. I'm about to prove now, so I'll just rub off from here to here. Okay, and I'll take the proof from here. Okay, so this is a property that has been taken now. Right. So let me prove here so that everyone can see. Proof: let A and B be two subsets of R such that A union B is equal to R and the intersection B is empty. Now I'll now use if here. I'll say assume that A is bounded above by B. Okay, so this means that every element B in B is an upper bound for A. Okay, you'll see. Let me record the line so that you can get this properly. This is A, this is B. A is bounded above by B. This is B. Okay, and we can also use the other way around to prove it by saying B is bounded below by A. But we are using one side proof now. Okay, from here to here. Okay, so now since we have assumed that A is bounded above by B, it means every element in this set B is an upper bound for this set. If I pick an element here, okay, this element here, if they are here, they are upper bound for this set. Okay, what we now follow is the completeness axiom. So I'll now say by completeness axiom. Someone should tell me what will be next now. By completeness axiom, what will happen? By completeness axiom, what will happen? Somebody should tell me that. Okay, what is not clear? Is it the definition or the camera? What is not clear? Then let me know. Popola. I'm with you now. What is not clear? Tell me. Yes. You know, look at this arrow. This arrow goes this way. You mean, if you are counting, we start from 1, 2, and we'll be moving in the right direction. Okay, if this is the same right as this, but it's showing me the left on the camera. I think this is your right. Is that okay? Okay, it means everything, since I'm moving this way, all the elements here are above this. Okay, because if I say, okay, here is 1, here will be 2. Okay, 2 is above 1, isn't it? So every element in B they are above A. That is the meaning. Yes, small b is the upper bound for A. Yes, those small b is the elements that are on this line. Okay, the capital B is a set. Okay, capital A is also a set. Okay, but I'm using small letter b there as element. Okay, to mean the number here, like that. Okay. So if this happens by completing axioms, if we have upper bound, okay, by completing axioms, there must be a list member among them. Okay, there must be a list member, and that list member is called supremum, and that's what we discussed in our last class. Okay. Okay, if there is a set that has upper bound, okay, that set must have a list member called the supremum. Okay, and then we'll say the supremum is these are element here, element B. Okay, are here. Among them, there is a list member. So because I'll be using alpha in the definition, okay, I'll call the list member of this to be, I'll call it alpha, and that alpha is nowhere but here. Okay. Okay, Toyin will say okay, all right. So by comparison, there is a list member. Okay, I'll call the list member alpha. There is a list member alpha. Okay, in R such that since alpha is a list member, okay, this is what will happen. Or is there anything the camera is not clear? Yes, sir. Understood, sir. Okay, let's hear from other people. Somebody is complaining about the camera. Okay, so let's move on. Okay, let me make it more clearer. Let me make it more clearer. If there is a way I can leave this diagram without removing it, so that I'll be using it throughout. This is A, this is B. Okay. Okay, let me also introduce element small a here. Element small a are here. Okay. Now this means that every element B in B is an upper bound for A. Okay, let's say that is, so that it will be, that is A is less or equal to B. Okay, for each A in A. Let's put it this way. Right? Now, by completeness axiom, B, that's those elements. The camera is clear. Thank you. It should be the person network. Okay. All right. Thank you. Okay. By computerization, B has that's all the B's. All the B's that are here. Okay. Let me use this. The B's, okay, have a list member. The B's have a list member, okay, such that alpha is less than B. Okay, because alpha is the supremum, it is the least of the upper band. Okay, and this is how it will be satisfied. Okay, you can check the previous note, and that's how we have defined it. Okay, I think you will get it from this. Now it means the at alpha, this is the least of the upper band. Okay, alpha is less than B. Alpha is here. All the other B's are here. Okay, now let me rub up this so I can make a conclusion now. Okay, now for any x in R, I want to make two assumptions with this. For any x in R, if x is less than alpha, okay, then x is less than B. And if x is less than B, this implies, okay, don't mind I'm using the arrow to mean implies. Okay, this implies x must belongs to A. Because if we have element that are strictly less than x, okay, sorry, if you have an element x that is strictly less than B, okay, it means that element cannot be any part of B. It will be part of A. Okay. Also, if we have x that is greater than alpha, okay, let's see the relationship between we have seen the relationship between alpha and B. According to this alpha is somewhere here. Let me put that in a box here so that I want to relate A and alpha together. A and alpha are like this, and this alpha is less than B. Now, what I'm now saying is, if S is less than alpha, compulsively S will be less than B. Okay. Now, if S is greater than alpha now, okay, look at this. These are related alpha and so any number that is greater than this, okay, alpha is less than or equal to alpha. Any number that is greater than alpha, okay, must be greater than A, because alpha is greater than A. Okay, so then S is greater than A, because this is bigger than this. Anything that is more than this is more than also this. Okay, and this implies that X belongs to B, and that's the conclusion of that theorem. Okay, the Dedekind theorem. Okay, so there are other versions of proof for this. Okay, so you can as well go through this again and again, and then let me know anywhere you are having issue. Okay, for the first time you are seeing this, you may not really get them, but when you look at them again and again, okay, you're used to them. Okay, line by line. So I think it is moderate to stop here, because after this we are moving on to another concept. Okay, that's a part B of this course. That is a sequence of real numbers. That is the next after this. So these are just the 4 properties of the number system we discussed. There are more than them. Okay, but for this course we have restricted ourselves to just 4. Okay, then we'll move on to another part B. Okay, this new part B. Okay, we'll be relying on all the assumptions we have made in the first part. Okay, so it means the first part of the note is very, very important. Okay, so we can stop here. If you have any question, let me know in the comment section before we leave. If there is no question, we can move on to maybe where are we resuming? Bolaji, is Bolaji there? Bolaji, Bolaji is no more. Okay, what about the other class rep? Okay, generally, is there any question? Babylon, any question? You are saying Omo. What is Omo here? Okay, no. All right. Yes, next week Monday is public holiday. Yes. So we are probably going to meet in 2 weeks' time. Okay, maybe next week Wednesday. Next week Wednesday, we can also meet. But I will discuss that in your group. Okay. So we can draw the curtain of the class. So if you have any other question, okay, you get let them get to me through the class. So thank you, everybody.